Yes, sir.
Yes, sir.
So y into integrating factor equal to integral right hand side. What is there in the right hand side? Q into integrating factor into dx plus c. To compute this c, you will be given sometimes something like y of 0 equal to 1 or y of 1 equal to something like this. Okay, so that we can use this condition to find out this integrating constant c. Okay, suppose if this function p is complicated, then this finding integral pds is difficult, or if this q is complicated, then finding this integral will be difficult. Okay, so in that case we will be trying to find the numerical solution of ordinary differential equation. So initially they have started with the first order, but there are some there are, and they improved for higher order like second order, third order, etc. But I think in your syllabus only first order is included. Okay, they doesn't talk about the higher order, so we will see only the first order in your class. Okay, so there are different methods are there. A number of numerical methods are available for the solution of first order differential equation of this form: dy by dx equal to f of x comma y given y of x0 equal to y0. Okay, so this is something like y of 0 equal to 1. Some condition is given. So if first order is given, we will be given one condition. If second order is given, we will be given two conditions, because in second order we will be getting two integrating constant. So to find out that constant, we need at least two. So two conditions will be given. So in general, the nth order differential equation, we will get n conditions. Okay, and these methods yield solution either as a power series in x, from which the values of y can be found by direct substitution. So we are seeing what are the different numerical methods. So some numerical methods we will get some series. Okay, and in that you have to substitute the particular values of x and y to get the y value. The methods of Picard and Taylor series belong to the formal class of solutions, whereas those of, so we are going to learn these methods in our syllabus. Okay, first method Picard, then Taylor series method, then we will learn Euler method, then there is something called modified Euler's method, then Runge-Kutta method. Okay, and this and all not included in our syllabus, Adam-Basforth method, etc. So there are two things. This numerical solution itself, we can split it into two types. In the first type, we will be getting some power series. Okay, and from which the values of y can be found by direct substitution. In that series, you substitute the x value to get the y value. So actually, this Picard method and Taylor series method belongs to this first type of method. In the second type of method, a set of values of x and y are given. Okay, so something we'll be computing step by step. For example, at 0 is the value is given. You will be asked to compute what will be the value at 0.5. Okay, so we will do step by step. We will not get any series here. So we will take h equal to 0.1, compute the value at 0.1. Then you compute the value at 0.2. Then compute the value at 0.3. Then at 0.4. Then at finally 0.5. So because of this reason, sometimes this method is also known as step-by-step method. So we are not computing the value in the single step. We are using h value to compute the value in multiple steps, not in a single step. Whereas in the first method, we will get some series. There you substitute the x value to get the y value directly. And this Picard's method and Taylor series method are the series method. The rest of the method are the step-by-step method. Can you understand the difference between these two?
Yes, sir.
Okay, first method, there is a series. There we will substitute x and get the answer. Second type of method, we will compute step by step in short steps. So for example, you can take 0.1, then you do it repeatedly. Then at 0.5, you will get the answer. So now let's see one by one. So Euler and Runge-Kutta methods are used for computing y over a limited range of x values. This Miles method, Adam-Basforth, is not in the syllabus. Okay, so I will avoid this one. So the initial conditions in y is specified at a point x0. So this type of condition, y of x0 equal to y0, is called initial condition. The initial condition is specified at the point x0. Such problems in which all the initial conditions are given at the initial point only are called initial value problem. So these problems are known as initial value problems, where we will be given the initial condition specified at only one initial point at x0 here. But there are some problems involving the second order and higher order differential equations in which the conditions may be given at two or more points. As I told you earlier, if you want to solve the second order ordinary differential equation, you need minimum two conditions. Okay, and these conditions are called boundary conditions, and these problems are known as boundary value problems. So if the condition is specified only at one point, that is called initial value problem. If the condition is specified at two or more points, then that is known as the boundary value problems. Okay, in this chapter we shall first explain methods for solving initial value problems, then give a method for solving boundary value problems. But this boundary value problems is not there in your syllabus. You have got only the initial value problems. Okay, that is, in all the problem the condition will be specified at only one point, like this: y of x0 equal to y0. So basically this is your problem. Okay, so at x0, when x equal to x0, when x is x0, the corresponding y value, that is y0, is given in the problem. This is given. So we have to compute the value of y at x equal to x1 or at x equal to x2, etc. That x equal to x1, x equal to x2, etc. We have to compute the corresponding y value. So we have to compute what will be the value of y1, then what will be the value of y2, etc. Okay, and this x1 is nothing but, all these are at equal interval. So meaning x1 is nothing but x0 plus h. X2 is nothing but x1 plus h, or x0 plus 2h, etc. Okay, so this is the problem. Now we will see, actually there are 5 methods are there in your syllabus. We will see one by one. Okay, so first method is Picard's method. Consider the first order equation dy by dx equal to f of x comma y. It is required to find that particular solution of equation number 1, which assumes the value y0 when x equal to x0. So what I do is, you multiply this dx this side, so you'll get dy equal to f of x comma y into dx. Then you integrate between the limits. So here this side y is there, so you integrate between y0 to y, and right hand side with respect to x, so you integrate between x0 to x. And if I consider the left hand side, if I integrate dy, what is the answer? Integrate dy,
Y.
y. What is the upper limit?
Y.
So if I substitute y, you will get y only, minus lower limit,
Y not.
y naught. So you will get y minus y0 equal to this integral, or you can bring this minus y0 to the right hand side to get this. Y equal to y0 plus integral x0 to x f of x comma y dx. Okay, but you see we are computing y only, but inside the integral there is some y, and this type of equation is known as the integral equation. This is an integral equation equivalent to equation number 1, for it contains the unknown function y under the integral sign. Y, we have to compute y only. Okay, but when I derive the formula for y, the formula itself we have got right hand side y. So to what we do is, in place of this y, we substitute y0 initially. What is the approximate answer for y? We know y0. So in place of this y, you substitute y0, and I call that as y1. This is nothing but the first approximation of y. After, then this y0 is some constant. Now this is purely in terms of x, that you can integrate, and then substitute the limits to get the value of y1. Okay. So in the next step, what we do, the same formula, in place of y, you substitute this y1.
Y1.
So you will get the second approximation of y1, that is nothing but y2. Is it understood? Then again, in place of y, you substitute y2. So we'll get y3. So continue this process, a sequence of functions of x, y1, y2, y3, etc. is obtained, each giving a better approximation. So y2 is better than y1. Y3 is better than y2. So if I proceed as many steps as possible, you will get more accurate answer, and you can stop up once you get the answer up to a particular approximation. Okay, for example, if you want to compute the answer correct to 3 decimal places, then check y2 and y3, you substitute x value. Okay, for example, assume that you want to compute the value of y at 0.1, correct to 3 decimal places. Then after finding y2, you compute the value of y at 0.1 using this. You will get some answer. Then after finding y3, you substitute 0.1. That is the third approximation of y. Suppose these two answers are same, correct to 3 decimal places, then you stop. Okay, so it depends upon how many decimal places you want to find the answer. But what is the main disadvantage of this method? We have got some integral sign. Okay, suppose the function is difficult, then integrating that function will become more difficult. So in that case, applying Picard's method will become a little bit difficult because you have to integrate something and the integration is difficult. So Picard's method is of considerable theoretical value but can be applied only to a limited classes of equations which the successive integrations can be performed easily. So we can apply this method to only those class of equations or functions where you can perform the integration easily. The method can be extended to simultaneous equation and equations of higher order. Okay, but that is not there in the syllabus, so I will leave the higher order. We will consider only the first order. Okay. So for example, you take this. This is the first problem. Using Picard's process of successive approximation, obtain a solution up to the fifth approximation. So you have to find out up to y5. y5 of the equation dy by dx equal to y plus x such that y equal to 1 when x equal to 0. So x0 is 0, y0 is 1. Check your answer by finding the exact particular solution. So we have to find using Picard's method as well as find the answer exactly. Then we have to compare these solutions. Okay. So what is the formula for y1, or in general what is the formula for y? Y equal to
Y naught plus
y0 plus y0 is 1 here. Okay,
yes.
so y0 plus integral x0. X0 is 0, x0 to x, f of x comma y dx. F of x comma y is y plus x. This is a general form. Dy by dx equal to f of x comma y. So in this problem, f of x comma y is y plus x. Okay. So to find out the first approximation, what we do in this, we substitute in place of y, we substitute
Value of Y naught.
1.
value of y, that is y0. So if I put y equal to 1 here, you will get 1 plus x. Now integrate this. So you'll get x plus x square by 2. Upper limit will become x plus x square by 2. Lower limit 0. So you'll get 1 plus x square by 2. Okay, this is first approximation. Then second approximation, what you do? The same thing. In place of this y, you substitute
y1.
y1. y1 is this. Okay, so here x is there plus x, so it will become 2x. Then integrate this again, so you will get the answer. Then third approximation, what we have to do? In place of y, you substitute this y2. So you'll get 1 plus x square plus x cube by 6 plus x. So you'll get 1 plus 2x plus x square plus x cube by 6. Integrate it, substitute the limits, you'll get the third approximation. Any doubt? Is it clear?
Yes, sir.
Okay.
Yes, sir.
In the same manner, you compute fourth approximation and
Can you repeat, sir, how it become 2x in second approximation?
here actually what we have to do, in place of y, we have to substitute
Why not?
y naught. So what is y naught here? Y naught is
1.
1. So I'll get 1 plus x.
Yes.
Integrate it. Next step, in place of y, we have to substitute
Y1.
y1. This
Okay,
is y1.
got
So
it.
this value plus x. X plus x. 2x.
Okay, sir.
Similarly, in place of y, you have to substitute y2. This is y2. y2 plus x. So this plus x. So you'll get x plus x, 2x. Then integrate. Okay. Then you compute and then find the third, fourth and fifth approximation. This one. Fourth and fifth approximation, you stop up to this. Okay, this is a numerical solution. Now we have to find out the answer exactly. Check your answer by finding the exact particular solution. So for that, you take this equation dy by dx equal to y plus x. How will you find out the exact answer? You bring this y to the left hand side. You will get dy by dx minus y equal to x. We know that this is a first order linear ordinary differential equation. What is p here?
Sir, P1.
Minus 1.
Yes, sir.
Dy by dx plus py equal to q. What is q?
X.
Q is right hand side, x. So what is the solution? First you find out the integrating factor. What is the integrating factor?
Sir, e to the power p dx.
E to the power integral p dx.
Integration of p dx.
Okay, so we'll get e to the power integral p is minus 1, so minus into dx. So we'll get e power minus x. So this is the integrating factor. Okay, then what is the solution? Y into integrating factor equal to integral y into integrating factor equal to integral q into integrating factor dx plus c. Okay, then integrate this using integration by parts. Okay, then multiply throughout by e power plus x. You'll get y here. This will get cancelled. This will get cancelled. You will get c e power x. So you'll get c e power x minus 1. This is the solution. To find out c, the condition is given. What is the condition? Y equal to 1 when x equal to 0. So you substitute to x equal to 0 and y equal to 1. If x equal to 0, 0, e power 0, 1, y is 1. Okay, so value of c is 2. Now substitute this c here, you will get 2 e power x minus 1. This is the answer. This is the exact answer. So what is e power x? What is the series expansion for e power x? 1 plus x by 1 factorial plus x square by 2 factorial, etc. So in this exact answer, in place of e power x, if I substitute this, you will get this. So this is the exact answer. You see, up to fifth approximation, what we have got? We have got up to x power 5 by 1
60.
plus x square plus x cube by 3, x power 4 by 12, x power 5 by 60, x power 6 by 720. But there you see, so exactly up to x power 5, the answer coincides. Are you getting this?
Yes, sir.
Okay. So maybe if I proceed and then compute y6, y7, etc., you will get the more accurate answer. There it is 720, here it is 360. This is the exact answer. Okay. Therefore, if I compare these two, it is clear that the numerical solution, that is equation number 1, approximate to the exact particular solution up to the term in x power 5. Okay. Now suppose if you want to compute the value of y at x equal to 1. So what you do, you substitute x equal to 1 there. In fourth approximation, here you substitute x equal to 1. Here also you substitute x equal to 1 and compute fourth and fifth approximation of y at x equal to 1. So you will get this y4 3.433 and the fifth approximation is this. Whereas the exact value, to compute exact value, you substitute here. Put x equal to 1. You will get 2 times e power 1 minus 1 minus 1. You simplify, you will get 3.44. You see, the answer is very close. Fourth approximation 3.433. Fifth approximation 3.434. Exact answer is 3.44. Maybe if I compute y6, y7, etc., it will become more close. In place of 4.3, okay, maybe you'll get 3.440123, something like that. So you'll get, answer will become more close to the exact answer. Okay, this is a Picard's method. Another problem. Dy by dx is this. You see that this is not linear. You cannot write this in terms of dy by dx plus py equal to q, Leibniz form. Okay. Now find the value of y for x equal to 0.1 by Picard's method. So same thing. What is the formula? Y equal to y0 plus integral x0 to x f of x comma y dx. Initially, you put the value of y, that is 1. Put y equal to 1 here. You are getting this. Okay, so if I divide the numerator by denominator, this will become quotient plus remainder by divisor. So minus 1, if I integrate this, 2 by 1 plus x, if I integrate 2 times log 1 plus x, substitute the limits, you are getting this. First approximation. Second approximation, you see it's very difficult. Is it clear? Second approximation is
difficult.
So we cannot proceed further. Just to stop, which is very difficult to integrate. So we can maximum find only up to the first approximation, and this is the maximum possible closest answer we can find. Okay, so this is the main disadvantage of this method. We have to integrate that. Okay, so then it comes Taylor. Taylor has found that he invented some other method. That method is nothing but Taylor series method. He also find the answer approximately, but there he avoid integration, he get differentiation. That is the next method, Taylor series method. Okay. Very simple. You write the Taylor series of some function. Okay, so that is y of x equal to the value of y at x0 minus x0 into y dash of x0. This y dash of x0 is nothing but what is y dash? This is y dash. Y dash is this f of x comma y. Okay, so y dash of 0 is y dash at x0 y0. Then x minus x0 whole square by 2 factorial y double dash of x0. Then x minus x cube x0 whole cube by 3 factorial y triple dash of x0, etc. Okay, so this is also this Taylor series you know already, right? You would have studied in first year. Taylor series, Maclaurin series, etc. Right? So now what you do in this series, you substitute x equal to x1. Then what you'll get? Y at x1. That is nothing but y1. So what is y1? y0 plus, if I substitute x equal to x1, what is x1 minus x0? What is x1 minus x0?
Sir, x1 minus x.
What is x1?
x0 plus h.
x0 plus h. So what is x1 minus x0?
H.
So in place of, if I substitute x equal to x1 here, you will get x1 minus x0. So that is h. H into this, I write it as y0 prime. So what is the notation? What is the meaning of y0 prime? The value of y prime at x0 comma y0. Okay. Then similarly here what you will get? x1 minus x0. So it is h square by 2 factorial h square by 2 factorial. You will get y0 double prime. What is y0 double prime? D square y by dx square at
d by dx of y dash.
You differentiate twice. You whatever y is there, you find d square y by dx square. There in place of x and y, you substitute
X not y.
x0 y0. Okay, you will get this. Similarly, in this term, if I simplify, what you will get? Third term. H cube by 3 factorial.
y0.
y0 triple prime. It means in the third derivative, you substitute x0 y0. This is a formula for y1. Similarly, what is the formula for y2?
Sir,
Instead of y0, we write y1.
y1, that's all. y1 plus h into y1 prime. y1 prime is nothing but dy by dx at
x1 y1.
x1 y1 plus h square by 2
Your
factorial.
audio is distorting.
What? Hello. So you will get the same formula, but whereas wherever y0 is there, you replace with the y1 etc. Okay, and y1 prime is nothing but y prime at x1 y1. Y1 double prime is y double prime, you substitute x1 y1 etc. Okay, so that's all. This is a Taylor series method. So since it is an infinite series, you can take as many terms as possible to get more accurate answer. So now you take this problem. Find by Taylor series method the value of y at 0.1 and at 0.2. Correct to 5 places of decimals from this equation. Okay. So what is this is dy by dx equal to f of x comma y. Okay. So y prime equal to x square y minus 1. So how will you find out the second derivative? Y double prime equal to, you differentiate this.
X square y minus 1.
Differentiate this. X square, if I differentiate y, it is y prime plus y into, if I differentiate x square, it is 2x. If I differentiate minus 1, 0. Then again you differentiate, find third derivative and fourth derivative. So it depends upon the problem also, you can choose. Suppose it is 6 or 7 marks, you try to compute up to the four derivatives. Suppose it is 3 or 4 marks, you can stop up to third derivative itself. Okay. Now, then what you do, you in all this, you substitute x0, y0. In y prime, you substitute x0, y0, you will get this. In y double prime, you substitute x0, y0, you will get this. X0, what is x0 here and what is y0 here? That is a given condition. What is x0?
0.1.
No. At what value the value of y is given?
Sir, 1.
Y at 0 is given. Therefore, x0 is 0. The value of y is 1. So, y0 is 1. So, this will be given. Y of x0 equal to y0. The value of y at x0 is y0. So, here x0 is 0, y0 is 1. We have to compute the value of y at 0.1 and 0.2. So, that is, you take x1 equal to 0.1 and x2 equal to 0.2 and then compute the value of y1 and y2. What is h here?
0.1.
0.1. Okay. So write the formula for, you instead of writing this formula, you write the formula I told you earlier, that is y1 equal to y0 plus h by 1 factorial y0 prime plus h square by 2 factorial y0 double prime, etc. So there you substitute up to the 4 derivatives, simplify, you will get the answer. Okay. In the book, actually what they have done is they have found y of x. Then that they have substituted 0.1 and 0.2. Okay. This is also correct. But if I use, when you compute y at 0.2, that is if I compute y2, here actually we have used only x0, y0. But in place of x0, if I would have used x1 and y1, you would have got the answer more approximately. Okay. Are you getting the difference between these two? Let me repeat it once again. Here what they have done? Here they have done only this y0 prime. They have found only the derivative at x0, y0. They substitute everything here, simplify. And here itself they substitute 0.1, 0.2. Okay. But instead of doing in this way, when you compute y at 0.1, if I use only x0, y0, and when I compute y at 0.2, if I use this x1 and y1 in place of x0, y0, your answer will become more accurate. In place of 0.80, maybe you will get 0.81 something. Okay, but this answer is more accurate than this one. So H you have to choose as small as possible. That is the thing. Okay. Problem. Employ Taylor series method to obtain approximate value of y at 0.2 for the differential equation. This y of 0 equal to 0. Compare the numerical solution obtained with the exact solution. Okay. So here also y prime is given. So differentiate and find y double prime, y triple prime, y fourth derivative, etc. And there you substitute x0, y0. What is x0 and what is y0 here? X0 is
0,
Sir,
0.
x0 is
0.
y0 is
Y0 is also 0. So you substitute 0 here and compute. Then write the Taylor series formula. So you see here they have got up just to y of x. Here itself we can substitute 0.1, 0.2, whatever it is, and then get the answer. Okay. But the better method is when you compute y1, you use only x0, y0. When you compute y2, again you recalculate y prime, etc. at the x1, y1 instead of x0, y0, and then use that answer will become more approximate than this one. Your BS Grewal book they were given in this way. Okay, but whatever numerical analysis book if you refer, they would have done this method only. Which method? What is the formula for y2? That will be in terms of y1. That is y1 plus h by 1 factorial, y1 prime, etc. y1 prime is nothing but in y prime you replace x1 y1 and then get the answer. That's all. Then in this method also we have to compute the exact answer and then compare. So to come exact answer is use this method dy by dx plus dy equal to q. Okay, integrating factor is this. Apply the given condition to get C. This is the answer. So if I put 0.2 here, you see this is what you have got 0.8112. Okay, but here exactly the answer somehow coincide, but the better method will be what I told you earlier. So maybe if you do it in that way, instead of 0 here, maybe you will get 1 2 or something like that. Okay, maybe 1 7 or 1 8. That will become more or less this one. Okay, that's all. Then this problem. Solved by Taylor series method, the equation this for y at 1.1 and 1.2 given y of 1 equal to 2. Okay. So here the differentiation is difficult. So they have computed only up to the third derivative. So this is the main disadvantage of this Taylor series method. So if the function become little bit difficult, then finding the successive differentiation will become difficult. Okay. So in Picard method, what is the problem? The problem is with
Integration.
integration. In Taylor series method, the problem is with differentiation. Okay, because we have to differentiate it successively. If the function is simple, then fine. Suppose the function is complicated, finding derivative will become difficult. Okay, so in that case, we have to look at some other method where neither differentiation nor integration is involved. Okay, so that method is nothing but Euler's method and modified Euler's method. Okay, we'll continue tomorrow. I'll stop up to this. Possibly by tomorrow or day after tomorrow, this syllabus will be over. So we have to learn 3 more methods. Euler's method, then modified Euler's method. Maybe these 2 tomorrow I will complete. Then there is another method called RK method that will finish it in day after tomorrow, so that this syllabus will be over. Okay, I'll stop up to this. You can fill the attendance and then leave. Yeah, fill the attendance.
Thank you, sir.
Thank you. Bye.
Thank you, sir.
Thank you. Bye.